Given a non-negative integer x, we need to return the non-negative square root of x rounded down to the nearest integer. We also can't use any built-in exponent function or operator, so that means we can't raise x to the 1/2 power or use a built-in square root function. So for example, if x was 100, then we'd return 10, since the square root of 100 is 10. But if x was 8, then we'd return 2, since the square root of 8 is around 2.83, and we need to round down to the nearest integer. Now, one way to do this is to just check every number one by one. So let's say x is 16. We would start at 0 and check if 0 times 0 equals 16. It doesn't, so then we check 1 times 1. And we'd keep repeating this until eventually we reach 4 times 4, which does equal 16. So now we know that 4 is the square root of 16, and we can return 4. Now this works, and since we start from 0, and we would only have to count up to the square root of x, this runs in O of square root of x time. This is not bad, but we can make this even better by using binary search. Let's say x is 16 again, which means that we know that the square root has to be somewhere between 0 and 16. Binary search starts at the number in the middle, which is 8. 8 times 8 is 64, which is too large, so we know that the square root has to be less than 8, so we can eliminate all the numbers greater than or equal to 8. Then we'll check the number at the midpoint of 0 and 7, which, when rounded down, is 3. 3 times 3 is 9, so now it's too small, so we can eliminate all numbers less than or equal to 3, and we'll go to the new midpoint. 5 times 5 is 25, which is too large, so we can eliminate 5 and anything greater, and now we finally reached 4, which is the correct answer. Now, binary search runs in O of log n time, and as you can see from this graph, an algorithm that runs in O of log n has a better time complexity than one that runs in O of square root of n. So binary search is the better approach. Now, why exactly does binary search run in O of log n time? Well, with each iteration, we eliminate around half the numbers until we converge on a single number. So the question is, how many times do we need to divide n by 2 until we reach 1? Let's say k is the number of times we need to divide n by 2 to reach 1. Then the equation is n over 2 to the kth power equals 1, and we need to solve for k. Let's move 2 to the kth power over to the right side, and we can isolate k by using logarithms, meaning that we can rearrange this to be log of n with the base of 2 equals k. So now we know that it takes log base 2 of n steps to complete the algorithm. But in big O notation, we ignore the base, so we say that this algorithm runs in O of log n time. Now let's look at the code and solve this in Python. Let's say x is 9, so we know that the square root is somewhere between 0 and 9. We'll establish two boundaries, left, which will equal 0, and right, which will equal 9. We'll use these two boundaries to narrow down the range of numbers. Then we'll enter a loop that'll keep going as long as left is less than or equal to right. So first, we'll calculate the midpoint number by doing left plus right divided by 2, then rounding down. So here, it's 0 plus 9 divided by 2, which is 4.5, then rounded down is 4. We're then going to multiply mid by itself to find its square. And at that point, three things could happen. The result could be less than x, greater than x, or if neither of those are true, then it must be equal to x. Now, I'm going to add a quick note here. In Python, we don't have to worry about integer overflow, but in other languages such as Java or C++, doing mid times mid may lead to overflow. So to avoid that, you could write this condition like this: if mid is less than x divided by mid. So we just divided both sides by mid, and the condition is still the same, but now there's no risk of overflow. And the same thing goes for this line here, where we do left plus right. But since we're using Python here, we don't need to worry about that, and we can just leave it. Moving on, mid times mid is 16, which is greater than x. So we'll jump to this elif block and update right to be mid minus 1, which is 3. Now we know that the square root has to be between 0 and 3, so we'll repeat this process. Mid equals 3 divided by 2 rounded down, which is 1. 1 squared is still 1, which is now less than x. So let's update the left pointer to be mid plus 1, which is 2. Next, mid equals 2, and 2 times 2 is 4, which is still less than x, so let's increment left to mid plus 1, which is 3. Now left and right are equal to each other, but we still need to do one more iteration to check that number. So mid equals 3, and 3 times 3 is 9. which is finally equal to x, so we can go to this else block and just return mid. And we have successfully found the square root of 9. Now let's do an example where x is not a perfect square. Let's say x is 7 this time. Again, we'll set up the left and right bounds to be 0 and 7, and now mid will be 3. 3 times 3 is 9, which is too big, so let's update right to be 2. Next, mid equals 1, and 1 times 1 equals 1. This is too small, so left will now be 2. Mid is also 2, and 2 times 2 is 4, which is still too small. This means we'll have to update left to be 3, and now notice that left is now greater than right. That makes this loop condition false, which means we weren't able to find any integer that is a square root of x. So at this point, we know that the square root is somewhere between 2 and 3. But since the question asks us to return the square root rounded down to the nearest integer, we can just exit the loop and return right. Now, why do we return right and not left? Well, if we've gotten to this part of the code, that means we've reached a point where left is greater than right. So if we return left, then we would be rounding up the square root. But since we need to round down the square root, we're going to return the smaller number, which is right. So the square root of 7 is around 2.6, and 2.6 rounded down is 2. And as you can see, right equals 2. So we return 2 and we're done.